We're not going to use any sort of new programming concepts. We've gotten up to packages. We're just going to go through now and do some plotting, go back over some of the things that we've already done. Start off sort of where we left off yesterday, building a linear model and interpreting the output of the linear model, running some correlations, looking at relationships between things, and we'll do it with some real data. And we'll take the data from the example that we used in the that I used in the lecture, and that data is in the DS Labs package, which you don't need to install again. So you just need to get it running. You just need to get those functions associated with the DS Labs package in the active working memory of R, of your R instance. So start by doing that.
Do you need to install it? What do you meant to write?
Install packages. Install dot packages. Yeah?
So each time you open up RStudio, you have to call the libraries again. It's not a default. Once you've done it, you have to call it again.
Exactly.
Can you make it a default? Or?
Generally, when you're working like this, you'll have a script, or
okay. Just run
and that'll be your sort of working document for that project. So you'll have a script associated with the project, and then normally the first couple of lines of your script will be library, something, calling up the packages that are relevant for that analysis. Are you having trouble?
It says labs quotation marks. It's not labs and then quotation marks. And does that normally what
For that autocomplete thing, like I notice a lot of people doing this, so we'll write it again. So you might write DS Labs, and then it auto-completes the second number of quotes, and then you have to erase that and go back here to do it. A good trick if you want to put something in quotes in R is to just highlight the word that you want to put in quotes and press the quotes button as if you're doing one set of quotes, and it'll put the whole word in quotes.
Okay.
Just a little useful tip. Okay, so let's load that up. And what data are we going to use? We're going to use some data called Gapminder. And this is some data from Gapminder's website, run by a famous sort of statistician who did lots of equality and poverty type outreach type research, who died recently, but there's lots of interesting data available from the data that he talked about and collected, and that's all been compiled and put into this Gapminder file. Some of that kind of data is in this Gapminder file, which is basically just world economic, social conditions and things like that. And if you want to know more about that, you can go to the blog that I showed you, that you should have the website for from exercise 2 in DS Labs. But this is fairly intuitive, the kind of data that's in this package. Sorry, that's in this particular data file. So let's look at it and just see what sort of variables we've got. So basically what we're looking at is each country for a year, the infant mortality for that country for that year, the life expectancy for that country for that year, the fertility, so the number of children born, the population for the country, the GDP for the country, and that's missing in this instance. That's missing data. So what happens is that normally for most functions that we call, that'll be filled with the average, the continent that the country's on, the region that it's in, and so on. So that's just a data frame. If you want more information, you can go !gapminder, and that'll tell you the health and income data. And it tells you what each of these variables mean. So infant mortality is infant deaths per 1,000. Life expectancy is in years, and so on. Okay? So that's the data set that we'll start working with, and it's a complex data set in the sense that it's got lots of observations. It's got 10,545 observations. So that means that there's 10,545 rows. That's going to be a little bit too much data to work with all at once, and there's going to be too many variables. So let's start with a simpler data set. And the data set that we'll start with is just the data for the year 2000. So let's just look at the year 2000. So make a new data frame. How would we do that? What would be the function that we should use?
Data.frame.
That's one way. There's another way.
Subset.
Subset. Yep. So the most efficient way at the moment would be subset. Subset Gapminder, where year is equal to 2000. And we don't need to put this in quotes because it's not text, it's a number. So R's going to go looking for a number. And we have the double equals here because we're interested in an equality that already exists. We're not telling it to be equal to, we're saying this is equal to out there in the world. So let's have a look and see what that looks like. Now we only have each country once. Before, these were all Albania because it was Albania in each year. Or maybe it wasn't, I can't remember. Now we only have each country once because it was measured only once in the year 2000. Okay, so let's start by looking at the relationship between fertility and life expectancy like we were talking about, and see if there's any relationship. So what would be the appropriate type of plot to use to start visualizing this? What sort of variables are these? Going back to our types of variables right at the beginning of the first lecture. A scatterplot, yeah. Yeah, because we've got two interval variables. Two variables where there's a meaningful distance between data points. So let's do that. And for that we just use plot. What did I say we want to look at? Life expectancy. Let's look at life expectancy. And here we're really just digging. We don't have any hypotheses. This is just sort of to look at plotting and to do some data exploration. So what do we see here? Is there?
Could you move it just a bit to the right so I can see the other graph?
Yeah, I knew that would be a problem. See if this fits. No, it doesn't. No, I've got to. There goes the whole thing. Okay. Sorry. The nice thing about R is when you close it, if you haven't saved something, it doesn't go away, hopefully. So there we go.
Just can I ask, could
Yeah.
you say where the data is taken from first and then plot what you want to plot it? So instead of saying like expectancy tilde, just saying data.
Yes, you
So
can. That's a really good question. So what you can do is, if you don't put anything equals to, like that, like I have here, then the function's waiting there and it's going to take arguments. So, and you can see which arguments plot can take. Plot can take lots of different types of arguments. So if we look at the help for plot, it takes an x coordinate or a y coordinate, or it can take a type which tells you what type of plot you have, title, all of that sort of thing. It can also take way more than what's here. It can take formulas, it can take data and all of that sort of thing. But if you don't put names on things, it's got sort of like a default order of stuff.
I was just wondering, instead in my
Yeah.
mind, I would say plot which data to take from,
Yeah.
and then what to check from this data set, I think.
So that'll only work if you tell it what argument you're providing. So here, if you put data first, my expectation is that this wouldn't work.
It makes sense.
So I'll show you.
Which data and then,
So that's not going to work.
okay.
So it's got a default order. And if you don't have a label like data equals, then you can't change that default order.
No.
So it's sitting there waiting for plot. So it doesn't know what to do with this yet. So I think if we did this, it might work. I think this is the right syntax. No. But if you have to say, this is the formula that I want to use, and this is the data that I want to use, then you don't have to stick to the default
You
order.
have to say what it should do and where to find the
Yeah.
data.
Yeah. Yeah.
If you use dollar sign, so data
Yes.
dollar sign,
Yeah.
column name, you also get code completion on the naming of the column.
You do?
Yeah.
Okay, yeah. So that you can see what you're working with.
Yeah, exactly.
That would be using this other syntax, which would also be fine for this sort of plot. That would be using this X column Y syntax.
Yeah, exactly.
Yeah. But I'm just sticking with this tilde
Yeah.
so that we're in the linear model.
You can also use the tilde.
Yeah.
Works the same.
So that's the thing with R is there's 100 different ways to do the same thing. So we,
And now you,
yeah, and this probably even works without putting data there, because that might be the order that it's waiting for. No. Oh, sorry. No, you need data.
You need to evaluate the whole script before see the open.
Ah, thank you. And it works. So because it's expecting the data as the next thing after you put a formula.
It's interesting because background and choose like you don't ask. It's not logic that you ask for the specific of what you want to do with the data and then ask for the data.
Because you're a statistician, you're just like, what am I going to do with my data? Now what data is it? You're more excited about the formula. Anyway. So we've got this plot. Which is hard to get to look nice for me. I think the first one looked nice. Okay, so we've got this plot. What does it mean? Can we say anything? What sort of correlation? Yeah?
If you want to live long, you shouldn't have very many kids.
Yes, so this is this causal inference.
Have a few.
Have a couple, not too many. I mean, rather than interpreting it in those terms, what else could it mean? What statistically, what does it mean? Is there do you think there's a correlation between these two terms, two variables? Can you make some predictions about what the correlation coefficient would be?
It's going to be negative.
It's going to be negative. This is always fun to do. Can you guess what the correlation coefficient would be just by how many clouds there are? What's your intuition?
None.
A correlation of 0.
No, but no intuition. So
Oh.
that's what the intuition would be.
Minus 0.4.
Minus 0.4, so moderate correlation. Okay, so let's test your intuitions. And the way we do that is with a function called core test. So this gives us both the correlation and the t-test for the correlation.
Is it core dot test?
COR.TEST. And we can see if the tilde notation works. That may not. I don't think it does. Make sure I haven't typed it wrong. Nope, so the tilde notation doesn't work. So we have to do it the other way, which is with the $ to pick out the array that we're interested in. So that would be dat 2000 $ life expectancy. And it doesn't matter what order you put these in, because we're just getting a covariance. And that gives us a correlation table. So what do these numbers mean? It means that there's a stronger correlation than you thought. So it's actually a strong correlation, it's not just a moderate correlation. T-value, what does that tell us? That's our test statistic for the correlation coefficient. And we get from that a p-value, which is the probability that there's this pattern of data given that there's no relationship between the variables. No association between the variables. This is our correlation coefficient, which is 0.8. So that's correlations. So let's do another one. Let's look at the relationship between life expectancy and population. Yeah?
Sorry, just if I read correlation correctly. So each time I have a chart, my life expectancy goes down 0.8. Is that correct?
No, that's the slope. Remember?
Ah, it's the slope.
Yeah. 0.8 is the spread of the data cloud. Right?
Yeah.
So if we square this value, that'll give us the r squared value, which will be the equivalent of the standard deviation of each data point.
Yeah.
From not the mean, but from a line through that data cloud. So it's good that you asked that question.
There are too many new terms, maybe.
Yes. Yeah, so you've got the direction, plus or minus, the data cloud, and the slope.
Yeah.
And they're three different things. So we can't say anything about the effect size here. We can't say anything about the specific nature of the relationship. So for each child, I will shorten my life by.
Okay.
We can't make that sort of inference from this.
No.
We need an effect for that. We need a slope for that. We'll come back to that.
So what does the t-value mean when you do it like this?
The t-value is the t-test for correlation coefficients.
Yeah.
And that is, I didn't go into detail with that, but that's something like the number of subjects with the square root of r divided by something, something, something. So don't worry too much about that. But the t-value is the test statistic for the correlation. So what the t-value means here is the effect that we're looking at. So the difference from just being a straight line through the data cloud, divided by a punishment on ourselves for how noisy the cloud is, how dispersed the cloud is.
Yeah, that was
Yeah.
I forgot the straight line.
Yeah. So that's what the t-value is checking.
So if they were on a straight line,
If they were on a straight line,
t would be 0.
if they were on a straight line, that was completely horizontal. T would be 0.
Yeah.
If it diverges from horizontal at all, t will be going up. Okay, so let's do the same thing for infant mortality, just to sort of explore around. Okay, so what sort of correlation is that? Well, I guess it'd be negative. Any guesses to its value? We'll have a look. It's probably going to be pretty high, I guess. 0.6? Yeah. 0.6? Okay, let's have a look. So it's minus 0.9. Sorry?
Yeah, so it's stronger.
It's stronger. Your intuitions are always going to be a little bit weaker than what the correlation coefficient is, usually.
That was the cloud, right?
Yeah, that's how cloudy is it?
Yeah. So, looking at the plots, I just thought this cloud was more cloudy.
It was more 0.6y looking. Yeah, but that's the thing. But there's an important lesson here, and that lesson is your intuitions about what the data looks like and what the numbers give you. And it goes both ways. And it doesn't matter how much experience you've got with data, you'll always, and I did it too, even though I knew what the numbers were, I'm like, oh, that's higher than I remembered. Even if you've got experience looking at these clouds, you'll still always find a correlation coefficient that's higher than you thought. And that means it goes both ways. If you see a correlation coefficient in a paper, that will, as you start to get used to data, that will paint a picture in your head of the data cloud that produces that produces that correlation coefficient. And you should always be aware that that data cloud is going to be fuzzier than what you're picturing.
Can you say something about, I mean, maybe the strong correlation is because at the low values it's very tight and then it gets more scattered. So would that mean anything for the prediction, that the prediction would be more precise?
We could make it even better, yeah. We could actually say that the fact that it gets scattered here, I think we could improve this correlation, and then we're going to come back to this figure at the end. Because maybe, I think it's this figure we come back to. We come back to a figure that looks a lot like this. Maybe this is not a straight line. So we can actually increase our correlation coefficient.
Yeah.
We can increase our R squared by trying a different model. And we'll come back to that right at the end. But the intuition for now is that your intuitions about what correlation coefficients look like is wrong. Correlation coefficients are always sort of nicer than what you picture in your head. And it goes both ways. So if you see a paper and you go, wow, correlation of 0.5, that's really high. I'm imagining sort of data roughly following a line. It's probably going to be a lot more scattered and splattered out than what you're thinking. And that's an important thing for understanding how we use this stuff.
How about the other numbers when looking at this table? I mean, the 95% confidence interval?
So the 95% confidence intervals, what that means, and I haven't talked so much about confidence intervals, but all a confidence interval means is, if we were to, and it's a misleadingly labelled statistic. So confidence interval, that would mean that intuitively you would say, well, 95% confidence interval, that must mean that we're 95% sure that the correlation coefficient is somewhere between 85 and 91%. Sorry, 0.85, negative 0.85 and negative 0.91. We're 95% sure that it's there.
Okay.
That's not really what it means though, strictly speaking. We're working in the frequentism world, and in frequentism, we're not saying anything about our beliefs. We're not saying anything about how sure we are, we're not saying anything about how certain we are. What we're saying specifically is, if we were to run this same experiment 100 times, 95 of those times, we would get a value between those two values. And that's where frequentism gets a little bit confusing, because it's not saying anything about our beliefs or our knowledge. It's saying if we could do this repeatedly over and over again, what we will find is this pattern, to avoid talking about subjectivity and try to keep things objective.
So is it related to standard error? That's the same idea.
No.
That you run
That's
it
it's
over and
yes,
over again,
yeah,
and you have the mean,
yeah.
means.
And I don't know what the mathematical relation is. It's not something I've ever really looked into. So I'll skip that question. Sorry. Okay. So let's do another plot that might have another interesting problem in it for us to deal with, a visualization problem. Let's plot life expectancy as a function of population this time. So how do we interpret that? It's not a very useful plot, is it? So here we've got a problem of scale. We can try and fix this a number of different ways. We can rescale our population and see if that helps. So put it on log scale. So let's do that.
Why did you do that?
So that transforms population from this massive scale where here we've got some countries that are extremely highly populated and some other countries that are still quite highly populated, and lots of countries that are sort of small to moderately populated. And that makes it really hard for us to see the relationships between these things. So what we'll do is we'll take the logarithm of this, and this is why logarithms were invented in the first place, to deal with this problem. We'll take the logarithm of this variable, and that will give us a much more easy to visualize data set. But now we have to remember that the x-axis represents the logarithm of the population, and not the population itself. So what do you think? Is there a relationship between population and life expectancy? No? Let's have a look. So no. We're seeing no relationship here. The t-value is very low. The p-value is almost 1. So that we're almost certain that we would get something like this if there was no relationship. Our 95% confidence interval, if we were to run our experiment, run this analysis again and again and again and again and again, we would get a correlation coefficient 95 times out of 100 between minus 0.14 and minus 0.14 and plus 0.14, and our estimated correlation coefficient is effectively 0. So there's no relationship. So the way you might use confidence intervals in this situation is you'll say, well, whenever the confidence interval is not 0, I'll say there's an effect. But whenever the confidence intervals overlap with 0, I'll say there's no effect. This is an alternative to using p-values, now that we've brought up correlation coefficients. So instead of using p-values, we might say, if our 95% confidence interval, if they're both plus numbers, so if we were to think of it as, if we run our experiment 100 times, 95 of those times we get a positive number, then we'll conclude that there's a positive correlation. Same as for negative. If we run the experiment 100 times, 95% of those times we get a negative number, we'll say there's a negative correlation. And then we can avoid using p-values. But we can't really, because there's a relationship between p-values and confidence intervals. So we can look like we're not using p-values, but we don't really do that. And this is related to parameter estimation. So this is where what you're more interested in doing is not hypothesis testing, but estimating the value of a parameter. So where you say, I'm not interested in testing whether or not I can reject a null hypothesis. I'm interested in testing the specific difference between two means, or the specific correlation coefficient, or the specific slope. That's sort of the parameter estimation framework, which is one alternative to null hypothesis significance testing.
So looking at the Scatterplot, then an alternative thesis would be to avoid a short life, you need to live in a small or a big country.
Or it just doesn't matter.
Well, actually, all the below 55 years seems to sort of
okay.
go towards the middle.
So what might be happening here is we've got another nonlinear relationship, right? We might have a U-shaped curve so that our straight line isn't capturing the data. Or we might have what's called a latent mixture. And this is a really interesting concept. We might have a latent mixture of two different kinds of nation. One with a curve like this, and one with a curve like this. And possibly one with a curve like this. So we might have a kind of country for which there's no relationship, a kind of country for which there's a straight line down, and a kind of country for which there's a straight line up. And that would be a different kind of model to just a straight line. So this is telling us that under the assumption that the only relationships that could possibly exist between population and life expectancy, there's no relationship between population and life expectancy. But if we don't hold that assumption, that conclusion might not follow. Okay.
Is there a way to compare models?
Yes. We'll
so
do.
So you choose which one is actually the best fit.
That's what we'll finish on today, model comparison. And we'll finish on the specific statistic that we use to test that. But it's very similar to R squared, the kind of thing that it's looking at. Okay? So let's start doing some models. Let's look at fertility. And here we'll use the LM function, which is linear model. And what this is going to do is fit one of those straight lines to the clouds of our data, like what I was showing you above. And the line that it's going to fit is the one with the lowest, with the highest R squared value, the lowest sums of squares, residual error. So the highest R squared value. And the way that it does that is analytically using some matrix mathematics, matrix algebra, that I don't know because I'm not a mathematician. I should probably learn it one day. So LM, life expectancy as a function of fertility in our data set. And that's going to make a new object that we've called fertility model, and we're using the same syntax as we used for our plots, but instead of plot, which inputs these arguments and outputs a plot, it's going to input these arguments and output a model object. So let's do that, and then we want to summarize that model object. And that'll give us our table. We don't want to summarize LM because that's the function. Okay, so here's our table. For this plot. So this is our table for the linear model, which is a straight line through this data cloud, the best straight line through this data cloud. And what this gives us is the formula we used, and our residuals. Gives us our median, our interquartile range, our minimum maximum values, which we haven't talked so much about, but basically that's the stuff that you use to make a box plot. And it gives us your model coefficient. It gives us the estimate of the model coefficient. So in terms of what we were talking about today, what does this number mean?
Does it mean how many years you'll live without children? Having no child? 0 children?
Yeah. So that's your intercept. So that's your baseline. So that's the effect of not including the predictor yet. So that's where the line that we've drawn on here will cross the x-axis. Sorry, the y-axis. And that's 82.18. That has a t-value, like we talked about, which we can put onto t-distribution to get a p-value, which is vanishingly small. So this is extremely unlikely to be due to chance. That this line is, that this is different from 0. This number is different from 0. Okay, so what's this? Yeah?
The loss of year per child.
Yeah, that's the effect of fertility. So for every child you have, you'll lose about 4.5 years of your life.
Just spill it out there.
I'm sure that's not true. Because there's a bunch of other stuff going on, right? There's hidden variables and all of that sort of thing, right?
So this would probably be driven by whether you have access to healthcare and can prevent pregnancies or not.
Exactly. And 100 billion
and
other.
whether you can live through childbirth.
And whether you can live through childbirth, yeah.
And there was also in Angola they have the most children.
Yes.
And they probably have the shortest.
And there's cultural things like religion and all of that sort of thing. And this is not my area. I do cognitive models. But there's a lot of other stuff that's going to be intervening. So this is not the sort of thing where we'd want to come out and causally say, policy, you know, like I was talking about at the end, policy suggestion. Make children illegal so that we can live for longer, which has got an obvious problem, right? Society's kind of going to stop. Our projector doesn't sound healthy. We can do the rest of the live demo, maybe. Sorry?
You can dictate and we'll
I can dictate. Exciting.
Something is
hands on
kind
track.
of clear.
Oh, good.
So somewhat.
So it's oh, there we go. There we go. Okay. So this value is your t-value. Do you notice anything about it? Why is it negative? Because it's a negative effect. It's a negative slope. And it also has a very small p-value. What's this? Okay, so what's this? The fit of the model. This is your R squared value.
How do we interpret 0.6? Is it a good fit?
So this is a good fit.
Why?
This is a moderate fit, I guess you could say.
From 0 to 1?
Yeah,
Okay.
but remember that it's R squared.
Yeah, okay.
So it's not an R value, it's an R value squared.
Okay, yeah.
And this has actually got a nice interpretation that we didn't have with R that now we get, which is this is the percentage of the variance that's explained by the model. Okay, so this is the percentage of the information, for want of a better word. So if you have a straight line, your model will explain 100% of the variability. And we're allowed to say that with R squared. So this model explains 64% of the variability. And if we had a better model, we might be able to explain more. So when we do model comparison, what we're going to do is we're going to look at something like this and see how we can improve by adding on new stuff.
So it's the same rule of thumb, 0.3 is weak, 0.5 is moderate, 0.8 is
roughly. Yeah. There's less discourse around cutoffs and norms for R-squared values. One, because it's got this more or less literal interpretation, and the other is that it hasn't been used so much. So at least in my fields, we've been using t-tests, correlations, and ANOVAs in different contexts, and R-squared is used in linear models, which reduces sort of all of those, well, at least t-tests and ANOVAs. So there's not so much discursive practice around interpretations of R-squared and cutoffs. But just a good way of thinking of it is it explains 64% of the variance. We also get a p-value down here. And what this p-value is a p-value of the entire model. So this is a p-value of your F statistic. And I'll come back to your F statistic later. I haven't talked about F statistics. But you can think of your F statistic as conceptually kind of similar to R-squared. It's not the same, but it's kind of similar. It's the sums of squared of the model divided by the sums of squared of the residuals. So it's a test statistic, which means that it's the effect divided by some punishing factor, leftover stuff that you haven't explained. And it's called an F statistic and not a T statistic because it falls on an F distribution and not a T distribution. So Fs happen to follow a distribution that, instead of looking like a normal distribution, looks like a big whale. That's an F statistic. And so what we do is we find our value on the x-axis for the F distribution, and it can't be negative. You can't have negative Fs because it's a positive number divided by a positive number. And here we have, what, 328. So to get a p-value, we just look at the area under here. And you can't have a two-tailed test. You can only have a one-tailed test because whales only have one tail.
They're always swimming in the same direction.
They're always swimming towards the left. Yes. Whales always swim from right to left.
The fertility is the slope.
Yep, fertility is a slope. Slope, intercept. So we can actually write out the equation now. We've got our formula for making predictions. And you see economists do this sort of thing. Psychologists never do this for some reason. But sort of empirical econ types often do this. So now we can say that y, our predicted y, is equal to 82.19 plus what? Okay, minus 4.45 x. There's our prediction. So we plug a value into here and we'll get a value out there with our slope and our y-intercept. So that means that I can put my age, sorry, the number of kids I've got in here. So let's just do that for fun. And we can see how long I'm going to live. So 82.19 minus 4.45. 2. Means that I'll get to 73.29.
With 64% chance.
Yes. Well, there's a 64% chance that that's right.
Yeah, that's correct.
Okay, that's right.
So how old am I going to get to? Just again, 70. I can live with that. That doesn't seem like a small number given my current age, but ask me again in 20 years. That actually might be the male life expectancy for Australians, so that's okay. Okay.
What is the multiple R squared compared to the adjusted?
The adjusted R squared, can I get back to you on that? I've forgotten what adjusted R squared corrects for. Do you know? Can you remember that? You can look that up. I can't remember if it corrects for number of parameters or something like that. It corrects for something and I've completely forgotten. Sorry about that.
They're very close to each other, so it's probably not that important.
No. They're not always. Yeah. What is it? I've forgotten. Yeah.
So what did the multiple stand for in multiple R squared?
We're looking it up.
Okay, sorry. Okay. Okay, it's okay.
Oh, what do the multiples stand for? We'll look that up too.
Okay.
Sorry.
All right. Okay. Sorry.
It's been a while since I've done frequency stuff. Okay, so let's do the same thing for the population. Let's make a population model. Takes the formula and the data as an input and spits out a model object, which we then need to get a summary of in order to get our table. And so we can go straight down here and see that this p-value is higher than 0.05. So there's no point looking at anything else. It doesn't even matter what the model parameters are. The intercept's not interesting, the slope's not interesting because the model itself is not significant. That kind of makes sense, right? Because we saw that there's no correlation given that model.
The adjusted R value.
Yep.
You use it when you use multiple variables in your model, and it adjusts it for if you add more useless variables that do not improve your.
Okay.
It will go down.
Okay. Yeah.
And so it's used for when you have multiple variables and when you need more samples.
Okay.
So that's what it's like the p-value which we were supposed to decrease the more you subsample.
Yeah.
Your
Yeah. So you're being punished here for having variables that don't add any explanatory value to your model. So you can think of it as Occam's razor.
And it can go as high as the R squared, or yeah, it can go as high as R squared and drop down. So it starts dropping.
Yeah.
Start picking out some
Yeah.
variables.
Yeah. So that's your Occam's razor, is having, you want the simplest possible model that's not too simple. And if you start adding junk, your R squared will turn to junk. Your adjusted R squared. Thank you very much for that. Sorry I didn't know. Okay. So that's about an hour's work. Should we have a break? 15-minute break?
So just one question. So the adjusted R squared would actually tell us if we added something and then it drops that we should take it out again.
Yeah. And there is a form of regression called stepwise regression, where you add and remove things and then watch how your R square changes, that we're not going to talk much about.